Welcome to part 4 of week 4. Biologists have made for a long time the distinction between continuous Fi curves, called type 1 or class 1, and discontinuous Fi curves, called type 2 or class 2. In fact, Hodgkin and Huxley introduced this distinction. But of course the question arises whether there are specific biological processes that make the difference between a type 1 or type 2 model, or whether we can understand this difference on some more general mathematical grounds. So let's start the discussion with our two-dimensional neuron model, and we have seen for the type of Kitsunaguma model that the W0 line would be a straight line, while the U-null line, the red null line, would have some more interesting shape. Now let's apply a stimulus. Let's apply a constant stimulus. A constant stimulus, as we have seen for the Kitsunaguma model, will shift up the curve. And if the curve is shifted upwards, what happens is that at some point the fixed point loses stability. Now, if the fixed point is unstable, and moreover, we can construct a closed boundary around it, then such that all arrows point inwards, then we know that there must be a limit cycle which corresponds to repetitive firing of the neuron. So the neuron fires repetitively, periodically, while on this limit cycle. So let's apply our constant stimulus. If we are down here, then we have a situation that corresponds to a stable fixed point with an inward circling trajectory. If we have a larger input, then we have an unstable fixed point with an outward circling trajectory. At some point there's the transition, and this transition corresponds mathematically to a Hopf bifurcation. The stability is lost at some finite frequency. There will be oscillations at some finite frequency that correspond to this rotational component here, and moreover, for the kind of Kitsunaguma model that we have considered here, the oscillation will be big. Importantly, we generate a discontinuous gain function out of this Hopf bifurcation. So let me discuss this in more detail. If you analyze the stability of the fixed points, we are first for zero input in a regime where we have a rotational component corresponding to the imaginary part of the eigenvalue, and we have a real part of the eigenvalue which is negative. This corresponds to this inward circling. If you just look at the voltage, it would show some oscillation, damped oscillations. Why? Because gamma, the real part of the eigenvalue, is negative. Now we increase our current. If we increase our current, then the real part of this eigenvalue increases. The eigenvalues sit at gamma plus I omega, that's this eigenvalue, and then there's another one, gamma minus I omega. It's down here. If I increase the constant external current, the real part increases, which means the eigenvalues move in the complex plane, and at some point they pass zero. And suddenly we have here a positive real part, gamma larger than zero. In this case, any small perturbation will blow up we have the oscillatory component corresponding to the imaginary part, omega, and we have a blow-up of the envelope, which corresponds to the real part of the eigenvalue, to gamma prime. Now, the bifurcation picture holds only in the direct neighborhood of this transition point. So as I increase my constant input, I'm first in the stable regime, then there's a critical value of the input, and then I'm in the regime where the fixed point is no longer stable. The linearization, the Taylor expansion around the fixed point is only possible in the direct neighborhood of the fixed point, and the analysis, the Hopf bifurcation picture, is only valid if we are in the neighborhood of this critical point. Now, two possibilities exist. One is that the oscillation itself is stable, and then this would correspond to an oscillation of finite size. So this amplitude of the oscillation would stabilize at some finite value. The fixed point is unstable, an oscillation develops, but the oscillation itself is stable. This is called a supercritical Hopf bifurcation. Or the other possibility, an oscillation develops, but this oscillation itself is unstable. However, there is, in the case of the Fitz-Nagumo model, another limit cycle further out. We know that there is a stable limit cycle, and this limit cycle corresponds to a large amplitude, to a much larger amplitude of the oscillation. This amplitude of the oscillation itself cannot be found through this linear stability analysis that we do here. To summarize, with a Hopf bifurcation, we have a transition from a stable fixed point with a rotational component to an unstable fixed point with a rotational component. For subcritical Hopf bifurcation, this unstable rotational component leads to a limit cycle of large amplitude, which we can interpret as a sequence of action potential as repetitive firing, and repetitive firing sets in as a finite frequency. At a finite frequency, we have a discontinuous Fi curve or discontinuous gain function. So, if we apply this in our case, for no current, I have the rotational component, I see it here, a little bit of oscillation, and the system goes towards a resting state for I equals 0. With a current larger than the critical current, the system is locally unstable, this fixed point is unstable, and there's a limit cycle, and if we start from this initial condition, we go on to the limit cycle, which corresponds to periodic firing. To summarize, a subcritical Hopf bifurcation, as we have it in the Fitz-Nagumo model, gives rise to a discontinuous frequency current curve. Now, what about type 1 models? Let's consider a slightly different scenario. The red node line, the U node line, is the same as before. However, the W node line is different now. Before it was just a linear function, now it's a function which itself bends and curves. And in this case, we would have three fixed points. A first fixed point here, a second fixed point here, and a third fixed point. It turns out that this one is stable, the middle one is a saddle, and this one is unstable. Now I've drawn some arrows. Here we have vertical arrows upwards, here I have vertical arrows downward. Now the size of the arrows gets smaller and smaller as we approach one of the fixed points. The same is true for the horizontal arrows. The size of the arrows gets smaller when we approach the fixed point. in the vicinity of the fixed point, the speed of the flow, the size of the arrows, is very small. Now we apply a constant stimulus. A constant stimulus will shift the curve upwards. There might be a slight change in the shape of the null line, but essentially it's a shift upwards. And if we shift the null line upwards, what we see is that these fixed points, they disappear. They disappear. Now, what about the flow errors? Previously we said, I have big flow errors here, I have big flow errors there, I have big errors here, I have big errors there. However, close to the fixed point, the errors were very small, very, very small. What does that mean? It means that if we are on a trajectory, so this is the new situation, errors are small. If the system is now on a trajectory, this is the remaining unstable fixed point. I have a bounding box with flow errors inside, so I know there's a limit cycle. However, the limit cycle passes through this regime where the size of errors is very small. There have been fixed points before. The fixed points have disappeared, but there's still something left, like the ruins of the fixed point. While we make this minor change in the applied current, a minor shift of the red curve, the size of the errors does not change substantially. That means the flow is extremely slow in this region, and therefore it takes a long time, a long time to close the limit cycle. Now this means that while the upswing of the action potential is rapid, while the downswing of the action potential is rapid, the neuron spends a lot of time in this region here. Therefore, the total time to complete the limit cycle is very long. The period of the limit cycle is long. That means the frequency of the limit cycle is very small. And right at the bifurcation point, at this critical current, the frequency goes to zero. The system spends a very long time in the neighborhood of the ruins of the fixed point. So the fixed points here have gone, but the ghost of the fixed point is still around. Now this low frequency firing is characteristic for a type 1 neuron model. Now here is an application, a concrete model. If the input current is zero, I have a stable fixed point here, and indeed the voltage trajectory goes to the stable resting potential. Now if I input larger than the critical input, starting from the same value, it goes on the limit cycle, and the limit cycle is fairly slow here. The fairly slow means that there is not a lot of change in an intermediate regime. If I make I larger than IC, but slowly approaching the critical current, then the system would spend a long time in this regime before it goes off to the next spike. Now all this was theoretical. I just drew, hand-drawn, some curve for the W null line. However, if you think of some activation dynamics, some gating dynamics, it would be quite natural to write down something like this here. And that would correspond more or less to the blue curve that I've shown on the right-hand side. So we have a bifurcation. We start off with 3 fixed points. We increase the current. The red curve shifts upwards. Only 1 fixed point is left. If this fixed point is unstable, we have a limit cycle, and the limit cycle is very slow in this region before it takes off again. Thus, we can identify a type 1 Fi curve with a saddle node bifurcation onto limit cycle, a type 2 curve, which means this continuous gain function can, for example, be generated by a subcritical Hopf bifurcation. How would you measure these curves? you use a constant current, nearly constant current, a very slowly increasing ramp current, so that you move very, very slowly along this axis. You see here firing starts at a very low frequency, firing starts at some finite frequency. To summarize, biologists have made a distinction between type 1 neurons, those that have a continuous gain function, those that are able to fire at very low frequency on one side, and type 2 neurons, those that have a minimal firing frequency and which have a discontinuous gain function. And of course, the question arises whether such a difference must be attributed to specific ion channels. Now, the mathematical analysis that I have presented, based on a long line of research of theoretical neuroscience, the analysis I've presented suggests that there are basic mathematical, as opposed to biological, properties that allow us to explain this distinction.